Adam, and boy do I have an amazing video for you today. So it's all about the top 10 most elegant Python one-liners that you can fit into a tweet. One-liners are something that all programmers love because it expresses so much information and such like complicated algorithms all in one line. So it's incredible. I've just finished updating this article, added loads of bits to it, so should be really easy for you to understand some of these like really complex ideas. And if you're more of a beginner, you should definitely enjoy this anyway, just to see the pure power of Python. But before we dive into it, please consider hitting that subscribe button and the notification bell to be notified whenever we post new videos. We are revamping the Thinkster site, getting YouTube up and running, so we'll be posting loads of great content now and in the short future. So without further ado, let's get into it. What is a one-liner? So as the name suggests, it's a snippet of code and solves a problem in a single line. If you want to learn how to write clean Pythonic code, understand kind of the intricacies of Python, then one-liners are the way to go. And we've compiled what we think are the top 10 most elegant ones. So here is a quick list of them. I will not go into them now because we'll just go through them one by one slowly. So the first one, how can we check if a string is a palindrome? So a palindrome is a sequence of characters or numbers, and it reads the same backwards as it does forwards. So for example, madam, or race car, or this number 10,201. If you read it backwards, 10201 or 10201, it's a palindrome. How can we check if something's a palindrome in Python? So let's have a look. We have this phrase Anna, which we can see is a palindrome. And really our one-liner is going to return 0 if it is a palindrome, or it will return -1 if it's not a palindrome. So we have this little function here, is palindrome equals phrase.find phrase and then slice notation : -1. And we can see if we print this result, we get 0, but if it wasn't a palindrome, then the result would be -1. So let's dive into that. What is going on here? So the key really is that it's using slice notation and the find function. So find function returns the start index of a given subsequence within some sequence, or usually, most commonly, it's used with strings. So for example, let's say we have the string, we'll just call it A, hello world. If we do a.find h, it should return 0. Boom, because that is in the 0th index. And if we do a.find e, it should return 1, because it's there. But if we search for a letter that isn't there, for example Z, we get -1, and that means it's not in there. But if we search for something a bit longer, like world, it will tell us the start index where world begins, so 6. And if we do a/6, we'll get W. Awesome. So that's the first thing. We can call it on any string in Python, and I think this is a good demonstration here. And then the next thing we need to do for this palindrome is slicing. So we've seen a quick example here, slice notation. Basic slice notation is this: start, stop, step. So it selects a sequence that starts at start, this is inclusive, and ends at the index stop, but that is exclusive. So it ends at stop -1. So for example, we know A6 is W, so therefore 7 has got to be O and 8 has got to be R. So we do A7 and then A8. Brilliant. But if we do A6 to 8, it's only going to select W and O because 8 is exclusive, so it just selects 6 and 7. And the final thing we can define is a step, which defines like how many characters you skip before selecting the next one. Or so if we do A starting from the start, to letter 8 again, but we only select every other character, then it's going to select, right, let's just print out A again. So you see it selects H, misses E, selects L, misses L, selects O, misses the space, selects W. So if we have a step of 2, selects every other character, the default step is 1. So you can also set a negative step size, which is what we do in the palindrome. So we select phrase : -1, which means we're selecting like from the start. We're not specifying a start or stop index, which means we're going through the entire phrase, but we're going through it backwards, -1. So if we do A : -1, it will print out hello world backwards. And the key here is that a palindrome printed backwards will be the same. So if we have, we set B as Anna, we do B : -1, it'll be Anna again. So this is why we're finding, we pass it the palindrome, and we pass like the phrase, we pass the find method, the palindrome, and we see if that returns 0, because it will return 0. It means it begins at the start, that's the start index, and then it'll be correct. And if it's not, then it will return -1. So for example, if we pass in a.find, so remember A is hello world, and we're just going to pass in this, is this phrase in there? No, and that's the same as a.find, A : -1. But if we do B, remember that's Anna, if we do B.find Anna, that's the same as B.find B : -1. Boom, there we go. Okay, one-liner number 9. We're going from easiest to hardest. So this one is slightly harder than the first one. And this is swapping two variables. Now this is something that Pythonistas love, because you can't do this in many other languages. And it's just a really, really nice way to do it. So we have A is hello, B equals by, and then the one-liner to set A equals by and B equals hello is just AB equals BA, with a comma in between them. Super, super, super easy, and like very intuitive. Most other languages require you to do something like this. So we have to create a brand new variable C, which equals A, and then we have to set A equal to B, and then B equal to C. And C is just there just to store the value of A while both A and B have the same value. So that's kind of annoying, and we've literally removed 2 lines from our code, and it's really easy to understand. So that is an excellent one-liner. Really recommend using that wherever you can. Okay, going back to some slice notation now. One-liner number 8. We want to sum over every second value in the list. So if you remember from earlier on, where is it here? We set a step size of 2 to go over and selected every second value. If we select a step size of 3, we select every third value, and so on. So we have some data here. Stock prices. Let's copy and paste this into our IPython shell. Brilliant. And we just want to we want to sum over every second day. So we want to add 23, 26, 41, and 35 together. So we can do that using sum, and we can use slicing to select every second one. So we do res equals sum, stock. Oh, see, I press tab then. There we go. Stock, we press tab, and it finishes it for us. Boom, and we print out res, we get 125. So that should be the same as 23 plus 26 plus 41 plus 35. And lo and behold, it is. Fantastic. So this slicing notation is the same as the palindrome one. And if you want more slicing tips and tricks, Thinkster actually has a slicing book. Check out the link to the article and get the slicing book there. We'll also put it in the description of this video. Really, really helpful. Slicing is incredibly important for any kind of coding that you're doing. Okay. One-liner number 7. So reading lines from a file and storing them in a list. Obviously, it's really important to be able to use files in your programs because we want to be communicating with the outside world. We might need to write some files. We might want to read some files. And this is a nice way to do all of that. So what we're going to do is, so I've already stored the file Zen of Python. I've created the file zen of python.txt. So if you don't know what the Zen of Python is, you can type import this into an IPython terminal or just a normal Python terminal, and you'll be able to read it. This is basically the guiding principles of Python and what they should be, and we'll come back to this later. But what we can do is we can store all of this in a file. So let me just quickly find where it is. So look, I've got it here, stored here in my code folder, and current folder, there's a little IPython trick. You can press exclamation mark, and it prints where you are. So PWD stands for print working directory. So I'm pretty sure I'll be in the home directory. For some reason, it is sometimes a bit slow. So let's just open this up. Ooh, does it return something? No. Side note, I'm using iTerminal, iTerm2. If you have a Mac, would really recommend this. It's like a really, really good terminal to use, and it really helps. So we're in users/Murphy. So what I'm going to do is get file name equals, and then so I need to select, this is Murphy, so I need to select code, and I'm going to select zen of python.txt. And what you can do is just copy and paste this, so do import this, copy and paste all of that into a text file, save it in your working directory, and then save that as the file name. Then, in order to get this into a list for us, we just simply do lines equals line.strip, which, so strip removes any white space before and after the string. For line in open file name. Now, this does work, but we'll get onto this in a second, that it's technically not best practice, and I'll show you what best practice is, but it is nice because it is a one-liner. And then if we just print lines out, we see, boom, we get everything there. Now, you can remove this white space if you would like, and that's what I did actually in the article. You'll see that the second thing here has been removed. But this is nice. It uses a list comprehension, which are incredibly, incredibly powerful and one of Python's like most loved features. So if you haven't seen a list comprehension before, it's quite similar to a for loop. So we could write this as a for loop. Let me just make this bigger. Cool. So we could write for line in open file name, line, like you do line dot strip, and then we want to like append this to some kind of empty list. So what we would have to do is like empty list, which we haven't created yet, but this is just for, we'd have to have some kind of list defined before this and do it. So you'll see here that Python will get confused because empty list isn't defined. There, and now we do it. So we define some empty list, for line and open file name, empty list.append this, and now we see that empty list is no longer empty. It contains everything. But that takes 3 lines. List comprehension takes that into 1 line. We don't have to define this list, and we don't have to add this append call. We simply give our list a name, assume it exists by writing some brackets, and then we just write the exact same as a for loop, but in the opposite order. It takes a bit of getting used to, but the idea is just expression, so this is what we want to do, and then the context, which is usually a for loop. And then if you want, you can put if statements and else clauses there as well. We do have a more in-depth tutorial on the site, so check that out in the article. Now, this is nice, but like I said before, it's best practice to, if you open anything, to also close it. So really we should have a close call here, but it's a bit strange because it's within a list comprehension. So the best way to do it is to use the with statement. So when I first saw this, I thought it was a bit confusing, but it basically means with, it's a context manager. So you'll see here, with open zen of python.txt as f, that means we're going to open this file and we've bound it to the local variable f. So therefore, we're going to write colon, and anything within this indentation block we can call f, and it's the exact same as open zen of python.txt. So you'll see that this line here is the same as this line here, except we've swapped open file name for f because we've bound f to this open file name. And when you exit this with statement, it automatically closes the file for you, so you don't have to type in, close file name or anything. Oh wait, whoops. Anyway, regardless. So yeah, this is how it works. Like, I rarely, you see, I'm not even sure. I typed in the wrong thing there because I never use this. I always just use the with statement, and it works the exact same way, as you can see here. Okay, moving on to one-liner number 6. Let's calculate, and let's clear this. Let's calculate the mathematical factorial function, so n exclamation mark. I always thought this was really funny when I first saw this. Like, if you're writing like 5 factorial, it's like 5 because it's 5 exclamation mark. So this is often asked at programming interviews, so really good one to learn and bear in mind. So we're going to use the reduce function. So this is a bit of a controversial function in Python. The creator of Python himself doesn't really like it and says that a list comprehension is almost always better, and it can be a bit abstract. So I think this is actually why we use the reduce functions in one-liners, because it's so powerful and does so much. But as you'll see, as we're getting more and more complex, we'll see that actually it's so much easier to read if we write these over multiple lines. But it's still really nice to see that we can do them in one line. So this is the first time we're coming across a lambda function. So first off, we need to import the reduce function. It's no longer built in. In Python 2 it was built in, but in Python 3 it's not. And functools is a built-in library, so you already have it installed if you have Python. We're going to set n equals 100, and then the one-liner is reduce lambda xy x times y in the range 1 to n plus 1. So remember that, so if we just look at this range, it goes from start to stop. Start is inclusive and stop is exclusive, so that's why we add on +1 to make sure we get all the numbers from 1 to n, including n. And a factorial is, so we have 5 factorial, that's the same as 5 times 4 times 3 times 2 times 1. So that's why we're doing lambda xy, and this takes, so it takes 2 arguments, function and a sequence. So the second argument is the sequence, first argument is this function, and it applies this function to the elements in the sequence one by one and kind of reduces it down to a final value. So let's do this. So let's say we have range 1 to 6, so that selects the numbers 1 to 5. And what it will do is, let's just get this as a list. What it will do is it will take the first and second arguments, so x and y, and it's going to multiply them together. So it's going to do 2 times 1 and end up with, or rather 1 times 2 and end up with 2. And then it's going to take this value and go to the third one. So then it's going to do 2 times 3 end up with 6, and then it's going to go to the fourth one. So then it's going to do 6 times 4, give us 24, and then it's going to go to the fifth one and do 24 times 5. Whoops. Oh, can't type today. 24 times 5, and give us 120. So hopefully that makes sense. And if we can define, one thing we can actually do, which I do slightly later on, is, well, so let's do it for n is 100 first off. N is 100, factorial equals reduce lambda x y, x times y, range 1. Cool. And let's print this out. We see this humongous number because n is 100. So lambda as well is an anonymous function. So this is just a nice thing from Python to create functions on the fly. Otherwise, we can do the exact same by defining a normal function. So we can say define mult xy, and we can just do return x times y. And again, we can pass this to reduce instead, and it gives us the same answer. But instead of defining this function, we just define it very quickly here using lambda. So it's just it just saves space basically. And as well, best practice, whenever you define a function like this, you're supposed to write a doc string, and this just takes up more time, especially if it's just something quite simple like multiplying two numbers together. So one way we can make this one-liner better is by adding another lambda to the front of this. So we're going to do factorial with a capital F this time, just to differentiate it, lambda n. So that means that the input to factorial is going to be some number n, and then we'll be able to call, as you can see here, factorial 3, and it will give us the answer to 3 factorial. And factorial 10, it will give us the answer to 10 factorial. And the rest is the exact same. This lambda just makes the whole function callable, and so it means that we don't have to define n outside of it, and it actually gives us a function that we can use. So I'm just going to copy and paste all of this for speed. Awesome. And now, if we have factorial 10, so we get that, and we have factorial 5. We know that's 120 because we calculated it above. Boom, there we go. So that's a really, really nice way to do it. I would also recommend try and figure out how to do it without reduce. That's a really good way to improve your skills. Learning how to, reduce is useful to understand, and then learning how to understand it without, because some people really don't like reduce, like the creator of Python himself. So it's good to know how to do it both ways. Okay, one-liner number 5, profiling a Python script. So obviously, performance optimization is really important at any level, pardon me, but this is especially true when you're working on big projects. You know, if something takes 10 seconds to compute on your computer, that's fine, but if you multiply that 100 times, 1,000 times, then it can get really costly and really expensive. So we want to optimize our code as much as possible, really. And we do that by profiling. So the documentation from Python says, a profile is a set of statistics that describes how often and for how long various parts of the program executed. And so by doing this, we can find bottlenecks in our program, and see, oh, it's acting really slowly here. And then we can go to the program and see, find those bits of code and see why they're acting so slowly, and then we can improve them. So it's a really, really helpful thing, and really simple, this one. So this one's built in. Let's say we just have some file foo.py. We go to terminal, and we just type in, let's see, what files do I have? Here. So let's see what's in row 13. Okay, cool. So I've got a little file here that does row 13 encryption. So what we'll do is we'll do Python -m and then C profile row 13.py. and we will see it start running. Brilliant. Now we won't dive into like everything that happens here, just for kind of brevity, but there's good information online, especially in the Python documentation, about what all of this means. But it tracks your statistics, like what are called, how long each function takes to run, how many times you call it, all this good stuff. Really, really useful. It could be an article in itself, really talking about all these bits and bobs, but just wanted to make you aware of that with this one-liner, and that really, really recommend using it because it saved me and everyone at Figster like loads of time. Okay, one-liner number 4. We're getting quite complex now. This is by far the most complex one we've run into, and when I first came across it, it took me quite a long time to figure it out. So let's dive into it and see what it is. So we're writing a function that returns the power set of a set. So that is the set of all subsets of a set. And I've said the word set so many times. But so a subset of some set A is, let's say we have some set A, which is 1, 2, 3, 4. A subset is just a collection of elements that are all within A. So a subset of A would be 1, 2. Another one would be 2, 4. Another one would be 2, 3, 4. And so on. Another thing to note is that the set itself, A, is classed as a subset mathematically, by definition. And final thing is the empty set is a subset of every single set. And there's quite a lot of maths behind this, but that's just kind of the basic overview. There's also some maths saying that the size of a power set is always a particular size, but we won't go into that now. But if you are, this is really interesting. I actually studied this at university and really enjoyed it, so really happy that it's included in this article. So what we're going to do is first off state that it's actually not possible to define a set of sets in Python. So sets are, as you can tell from this notation, they're basically, the syntax is exactly the same as a list, but instead of using square brackets, we just use curly brackets. And the difference between a set and a list, a big one, is that sets only contain an element once. So if we do 1, 1, 2, 3, 4, it will return 1, 2, 3, 4. But if it's a list, it will return 1, 1, 2, 3, 4. And this is because another thing to note is that sets can only contain immutable objects. So we can also call these hashable objects. And that means that you can apply the hash function to them. Now, I would really recommend checking out our dictionary article for more info on hashing. But basically, you can apply it to anything, any immutable object in Python, and you get this number back. And in the background, Python applies hash to all the values in a set. And if you do an operation, for example, what have we got? So we have A as this. If we do 1 in A, it uses the hash value in the background to check whether it is or isn't. And we can see that 10 in A is false, but 1 in A is true. And it will always be that instantaneous when you do it, regardless of how big a set is. But if you do it with a list, it's a lot slower because it doesn't hash the values. And so this is one massive advantage to use sets over lists. But unfortunately, because of that, we can't actually have a set of sets. So our power set is actually going to be a list of lists. But don't let that worry. Don't let that confuse you. It's just kind of a bit of semantics here. So I actually think before we dive into this one-liner, you can have a quick read of it if you want. It is very, very concise and took me quite a while to figure out what was going on. So what we'll do instead is actually first write out a power set function over several lines, and understanding like what the process is behind creating a power set, because it can take a while. So, pardon me, just going to have a sip of coffee. So let's first manually create a power set. So it's the set of all subsets of a given set. The empty set is always a subset of a set. Therefore, the most basic power set is going to be this. So it's this set containing just the empty set, and that's the power set of this. Going one up from that would be the set 1. Oh wait, sorry. So this is the empty set. This is 1. So 1, we know the subsets of this are the empty set. Cool. And then we also know, if we go up from that, that 1 is in there. So therefore, that has to be in there. No, ignore the double notation. So therefore, the power set is going to be the set or list that contains the empty set and also contains 1. So this is going to be the power set of 1. If we go up from that, the power set of 1, 2, we can tell from the exact same reasoning as above, contains the empty set, also contains 1, and also contains 2. So we know that these 3 things are going to be in the power set. But also, as I've already said, the power set also contains the entire set as a subset, so that therefore it also contains 1, 2. So the final answer is the set that contains the empty set 1, 2, and 1, 2 together. So let's write this now as an algorithm in pseudocode to build the power set of 1, 2. So the basic process is that we're going to add. So we're going to start with a list of lists, and the list of lists is just going to contain the empty list to start off, right? So power set is a list containing the empty list, and we're going to recursively add each element of my set to every element that's already in the power set. If that doesn't make sense yet, hopefully it will in a moment. So my set is the set 1, 2. We start off with our base power set being a list containing just the empty list. We take the first value of my set, which is 1, and then we add it to every list in power set. So we've only got the empty list to do so we just have one sum. So we have empty list plus 1 equals the list containing just 1. Now that is now a subset, so therefore we can add it to the power set. So the way to do that is just power set.append 1. And if you type this out as I go along, this will really help. So now if you type out power set, you'll see that it is a list of lists, and the lists it contains are the empty list and the list containing 1, as we've just created. So next value in my set is 2. So we're going to do the exact same thing. We're going to add 2 to every list that's already in the power set. So they are empty list and 1. So we've got 2 sums to do. So we add empty list plus 2 equals a list containing just 2. And then we have list containing 1 plus 2 is list containing 1 and 2. And we're going to append both these results to power set. So we now have this power set empty list 1, 2, and 1, 2. Since we have no more elements left in my set to iterate through, so therefore we're done, and this is our final power set. So that's the basic algorithm we're going to follow. You may want to pause and rewind this to make sure you understand, but that is the process we're going to follow. And if we continue to do this, it doesn't matter how big our set is, we can just keep adding that single element to all the elements in the current power set we have, and once we run out of elements or values, we are then done. So let's try and code this up. We're going to be using the exact same process we followed above, but instead of doing powerset.append, we're going to do powerset plus this. So a list containing the list that we want to add to the power set. These are the exact same things. And the reason for that will become a bit clearer later. So let's go. So we know the power set is a set containing every subset, but we can't have sets containing sets in Python. Therefore, our power set is a list of lists. And we want to append the values in my set to each list in this list of lists. We keep doing this until we run out of values in my set. So, as a for loop, we can write it like this. So, remember, power set is a list of lists. So, for each list in our list of lists, we're going to append some value, which is from my set. So, this is the same as using this, changing this plus notation. So, for a list in our list of lists, we're going to do list plus value in brackets. And this is the same process that we've been following up here. Whoa, what's going on? Some classic Python lines before and during our for loop. So we're going to, first off, initialize an empty list, so our final list of lists, and then do the iteration above, so for list and list and list. The next list that we want to add is going to be list plus value. And then we're going to append this to append next list to final lists of lists. Or, in fact, what it should be is plus next list. However, we will then have to do this and reassign it. So this is the one issue in a for loop of writing plus. It takes a bit more time. So that's why it's nice to use append, but we're going to be using this notation in future, so we'll see. Also, as we've seen earlier, we can write our for loops as list comprehensions. So we're going to compress all of this down into the lovely list comprehension like this, using the exact same as we did for an earlier one-liner. So here it is, list plus value, boom, for list in list of lists, awesome. And then we initialize our empty list and add values to it in one line simply by just putting list brackets around it. So really nice. But, of course, we don't just want to add all the elements and leave all the elements that are in the power set already. We want to keep all the elements we have in the power set, plus add some new elements. So we add on our original list of lists to the start as well. So this is the code we have to do this process of adding on a value to all the elements in our power set already. And let's write this. We'll write this as a function with the most descriptive name I've definitely ever used. So we're going to call it add value to every list in list of lists. And the arguments are a list of lists and the value we want to add. So given a list of lists, return a list that contains the original list of lists and each list with value appended to it. So if we have, we want to add the value 3 to every list in empty list 1, 1, 2, and then return the original list of lists as well. So if we call this, what we want to get out is our original 1, 2, 3 elements, 1, 2, 3, and then we're going to add 3 to every one. So 3 plus the empty list is 3, 3 plus 1 is 1, 3, and 3 plus 1, 2 is 1, 2, 3. And we just write return this piece of code we've already written. Awesome. So to create a power set, we're going to apply this function recursively to every value in my set, starting with the base power set. So we've already covered this. So define power set, takes one argument, my set, and returns the power set of my set. So we initialize our most basic power set. So we'll call that current power set and set that to the most basic one, list containing the empty list. And we're going to iterate over every value in my set, for value in my set. And we take that value and add it to all the elements of the current power set using add value to every list in list of lists. And we set that to the current power set and value. And then we reassign current power set to this so that it gets updated over every iteration. And then we return current power set at the end. Whew, okay. That was pretty complicated, but hopefully you followed along. I would recommend watching this again if it didn't make sense the first time. The second time it will do. So let's test this out. If we now call power set on the empty set, we get back this. If we call power set on 1, like we did above, we get back this. And if we call power set on 1, 2, as we've done before, we get back this. 1, 2, 3, boom, it works. Copy paste this into your terminal, go through it. But hopefully that all makes sense. And now we're going to look at the one-liner and show you how that's equivalent. So the one-liner from above may be a bit complicated to start off with. So it's lambda L reduce lambda ZX, Z plus, Y plus X for Y and Z, L, and then the list of lists. So you may notice some similarities here, and they are incredibly similar. So we've replaced it with the descriptive names we've been using above. So it's lambda mySet, which is the same as power set mySet. Reduce lambda LOL, as in list of lists, value, which is the same as add value to every list in list of lists, current power set value. So current power set is a list of lists, so that's the same. And then we use the exact same list comprehension as we did in that function. We're going to iterate over mySet, that's the second reduce argument, and then our base set, our base kind of iterable that we're going to be adding all the values to is this, the empty set. So that, and then all we have to do is, to make this a bit shorter, is we can reduce all of these, we can swap all of these descriptive names for less descriptive names, boom, and then we get the one-liner. I personally found this one the hardest. Hopefully that all makes sense. Let's move on to one-liner number 3. Let's find the first n Fibonacci numbers. So what are the Fibonacci numbers? They are one of the most famous mathematical sequences, and they are the values in the Fibonacci sequence. So it has loads and loads of application in art, maths, biology, classically been used to model the population of rabbits. So how does this work? So the sequence starts with the numbers 0 and 1, and then every subsequent value is you add the previous two together. So 0 plus 1 is 1, and then 1 plus 1 is 2, and 2 plus 1 is 3, and 3 plus 2 is 5, and so on. So how can we create this using some code? So quite simply, we're going to use recursion here, and this might be a bit complex the first time you see it, but it definitely was for me. But once you work through a couple of these like recursion problems, they'll all start to make a lot more sense. So lambda x, will return, so that's an anonymous function. It returns x if x is less than or equal to 1. So, i.e., if x is 0 or 1, return 0 or 1. Otherwise, return fib x minus 1, as in it's calling itself, plus fib x minus 2. So remember, if we're trying to calculate like this value here, the 1, 2, 3, 4th value, then we have to, that is made up of the x minus 1 third, x minus plus x minus 2 second value. So that's what this is saying. And it's just going to recursively call this like over and over again until it gets to 0 or 1. And then there's just going to be loads and loads of 1s and 0s to add together. Well, loads and loads of 1s to add together, really. And then it will figure it out, basically. So for I in range n, print fib I. And then this will print out all the Fibonacci numbers like so. So this is just an explanation here. One thing to note is that it's a pretty intuitive way to calculate it, but it's really, really, really inefficient, because every single time you calculate the next Fibonacci number, it calculates all the previous ones from scratch. And so it would be way better to like store all the results in a list, so that you don't have to recompute all the values again. You just have to find like the previous two numbers and add them together to get the next one. So yeah, if you're trying to make an efficient Fibonacci sequence number, sequence creator would not recommend this one. Okay, moving on to a similar idea, the Quicksort algorithm. So we've actually got a video on the Quicksort algorithm in the article, so would recommend actually checking that out very quickly. It gives a really, really good explanation, and will make this much easier to understand. But basic idea is so. It goes like so. So I will quickly do it for you now. So we have unsorted. The first thing we do is we choose, all right, let's clear this just to make it a bit easier to see. So we're going to choose a pivot element. So we're going to pick the first element as the pivot element. If it wants to load, there we go. So unsorted. We're going to pick the pivot element. So that's going to be unsorted 0, 33. And then we're going to move all the elements that are less than the pivot element in front of it. So we're going to go through unsorted and find all the elements that are less than it. So all the elements that are less than 33, we're going to put here. So we're going to find 2, 3, 6. Brilliant. Then we're going to add the pivot element. So that's going to be 33 in this case. And then we're going to put all the elements that are greater than the pivot element. So if we go through here, we find 45 and 54. Boom. And then it just so happens in this case that our list is perfectly sorted. However, let's get another list, and we'll do 33, and then we'll do 12, 3, 45. Let's see, 1 and 54. So we've just changed a few of them. Again, we're going to pick the first element. And then, so it's still 33. We're going to find all the elements that are less than it and put them first. So we go through it, 12, 2, 45 is bigger, so no, and then 1. Cool. And then we're going to add the pivot element, and then we're going to find all the elements that are bigger than it. So plus 45 and 54. Great. So this is our list as it stands now. And what we will now do is on these separate lists, we're going to do the exact same thing. So now we're going to look at this list, 12, 2, 1. We're going to pick the first element, so that's 12. And then we're going to take all the elements that are less than it and put that first. So that's going to be 2 and 1 plus 12. And then we've got plus 33. Because we're still editing this, and then we're going to do the same quicksort algorithm on here. So we've got 45, and then we've got, oh wait, sorry. So yeah, in this case, so we take the elements that are smaller than 12, boom, then we put 12, and then we put all the elements that are bigger than 12 in this list, but there aren't any, so we don't add anything. So therefore, we're just going to continue with this line here. So then we've put 33 plus, and now we're going to apply quicksort to this as well. So we've got 45 as our first element, the pivot element. And we want to put first all the elements that are smaller than 45, which in this case is none of them. So we just put, so we don't put anything, but we can put the empty list. Yeah, let's put the empty list here as well. Plus empty list. So the empty list, because none are smaller than 45, then we put 45. And then we put all the elements that are bigger than 45, so in this case, 54. So now we are almost done. We have one more list we need to apply quicksort to. In this case, 2 is our pivot element, so we put all the elements that are smaller than 2 in this list to the left, so that's 1. Then we put our pivot element, which is 2. Then we put all the elements bigger than 2, which is none, so we put the empty list. And now all of these are singletons, as in there's only one element in each one. So we'll just copy paste all of that. Boom. We now have a sorted list. This is the Quicksort algorithm. So if you've understood that, you should understand the code. So here it is kind of written over a few lines. So if our list is the empty list, we're just going to return the empty list. If it's not the empty list, then we're going to apply quicksort to all the elements. So again, we're going to select L0 as our pivot, the first element, and that goes. So then we look at all the values x for x in L1 to the end, because we're ignoring L0 and just looking at all the elements from index 1 to the end of the list. And then if x is less than L0, cool. And then we add L0 into the middle. And then we do the exact same. So we do quicksort x for x in L1 to the end if x is greater than L0, which is exactly what we've been doing here. And we're going to move all of that into one line. So this code is the exact same. We're just kind of moving it all into one line and applying it as a Lambda function instead. So the input to Quicksort is L, so some kind of list, Lambda L. And then here we go, empty list if L is the empty list, else call quicksort again, and this is the exact same code we've just put here. And then boom, there we go. It works. So hopefully this kind of interactive explanation makes a lot of sense. I feel like that's probably the best way to understand it. And finally, we move on to the Sieve of Aristophanes. I'm not sure if I'm pronouncing that right. But this is a wonderful, wonderful mathematical algorithm, and it finds all prime numbers below a given number n. So again, Khan Academy explains it. We've got the link to the video. I would actually recommend pausing this video and watching it because it gives a really, really, really nice visual understanding of it. I'm going to explain it here in words, but I personally found it easier to understand just by visualizing it. Just having a sip of water there. So, what's the idea based on? So every single number can be written as the product of prime numbers. So this is called prime factorization. You may have done this in school. So for example, 30 is 2 times 3 times 5. These are all prime numbers. So the prime factors of 30 are 2, 3, and 5. You may also see that you can have more than that. So you can have like 2 squared times 3 cubed times 5 is 540. So the prime factors of 540 are 2 squared, 3 cubed, and 5. So a number is prime if its prime factors are just 1 and itself. So 19's prime factors are 1 and 19. So 19 is prime. Now, obviously, it's the case that for any number, so let's say 540, if we do 540 times 1, we get 540, but we can break it down into prime factors, and we ignore these ones. So we begin this algorithm by defining some number n, and we want to find all prime numbers up to, unfortunately, not including n. So what we're going to do is exclude all the non-prime numbers. So basically, we'll just be left with, the only numbers that will be left will be the prime numbers. So we start with all the numbers as unmarked, and we start from the beginning, number 2. If you come to an unmarked number, it means it's prime. So all the numbers are marked. Let's assume we're doing it for numbers, 1 to 100. We start at 2 and see that it's unmarked, therefore it's prime. So now we mark all the multiples of 2 as non-prime, because obviously they are then, you can get them by multiplying 2 together multiple times. So like we mark 4, 6, 8, 10, etc. all as non-prime. Next number we come to is 3. That's not been marked yet, so that is also prime. And now we mark all the multiples of 3 as non-prime as well. But, so that would be, 6, 9, 12, etc. But 6 has already been marked because it's also a multiple of 2. So we actually start marking from 3 squared. So start marking from 9. So we'll mark 9 as non-prime, 12 again, already been done, but that's okay. 12 as non-prime, 15 as non-prime, etc. So in general, for any unmarked number, i.e. a prime number, you mark all of its multiples starting from x squared. And if you find an x where x squared is greater than n, then you can stop. And all the unmarked numbers you have left are the primes, up to m. Really, really, really cool, simple algorithm. It's been around for over 2,000 years, and it works, basically. So again, here is the one-liner, and again, I think it's actually beneficial to define it as a function first, and then we'll go back to the one-liner. So here we go. Function definition, Sieve of Aristophanes. Whoops. Okay, return the set of all prime numbers below n. So all the numbers we're looking for are therefore in the range 2 to n, and we're going to make that a set. I'm going to call that all nums. And given that we start marking non-primes from x squared, we only need to check numbers up to the square root of n, because the square root of n squared is n. So we're going to check range 2 to the integer value of n square rooted. So these are the only numbers we need to check. And then we're just going to do it right as a for loop. So for x in numbers to check, if x is in all numbers, that means it's not been marked and therefore is prime. And what we're going to do here is note that if we mark a number, we're going to remove it from the set of all numbers. So we start off with all numbers. When we mark it, we're going to subtract them, get rid of them, and then the numbers we'll be left with will be the primes. So if x is in all numbers to start with, the first number we come to is 2. Then we're going to keep it and remove all the multiples of x from x squared onwards. So all numbers minus the range from x squared to n with a step of x. So that means that it's a multiple of x, and we're going to minus that. And then if x is not in all numbers, that means it's already been marked / removed already. So therefore it's a multiple of something. It's not prime. So we're just going to move on to the next iteration, next number to check, without any action. So let's just continue. And then finally, once this for loop is finished, we're going to return all the numbers. Perfect. So if we test this out, call it with 10, you'll see 2, 3, 5, 7. Oh, whoops, that's not right. Because 9, this isn't right. I think this still works. I think I've just put it down wrong. Nope. I see, Google doesn't like this. Okay, I think, well, I know this works because if we call it with 37, we see that these are all definitely prime numbers. So I think that's just a typo there. Let's now turn this into the one-liner. So here is the one-liner from the start. And instead of trying to read through this, what I've done is broken it down into its individual parts and shown how this is the same as this for loop here, as this function call here. So primes equals, it's the same as just defining our function name. Lambda n, so the input to our function is the number n that we want to find all the primes below for. Reduce, our good old friend reduce, so we're iteratively removing elements one by one and modifying the set, so we use reduce. This lambda call is the exact same as the first if statement in our function, which is here, if x in all nums. But because reduce works a bit like a list comprehension in terms of its syntax, we have to put if x in all nums at the end, and then we do all nums minus this, and it's a function, so we have to write, lambda all nums and x. And then The major difference here is that in our for loop we have else continue, so it means don't do anything, but reduce must return something on each iteration. Therefore, we just return the unmodified set if we find an x that is not in all nums. So we just return that, and that moves on to the next iteration. The second argument of reduce is the numbers to iterate over. So that's just the exact same as nums to check as we defined in our function, which is this. And then the third argument of reduce is the starting set, which we're going to modify. So that is all nums, and again is the exact same as the one in our function definition. So if you just join all those lines together, replace all nums with r, because you'll see here in the one-liner it says r, you will get the one-liner back. Whew! Okay, there we have it. The top 10 most elegant Python one-liners on the internet. Goodness me, that's a lot. If you can understand all of that, your coding will get so much better. You'll feel really confident, and you'll have some lovely, elegant code that you can write. But final word of warning, readability. So one-liners are amazing, they're powerful, and they can be really elegant solutions to problems. But they can also be pretty hard to read, especially if they're doing really complex things. And as the Zen of Python states, readability counts. So for a computer, it doesn't really matter if something's readable or not, but first and foremost, code is meant to be read by humans and understood by humans, and then computers second. So some of these one-liners, for example, AB equals BA, totally fine to use, but other ones, like for example this final one, the Sieve of Aristophanes, which I can't say, I would say you probably shouldn't be using these in your code, just because they are very difficult to understand, and something like this explicit function definition would be much better and really helpful for other people who want to read your code. But not even that, for you, 6 months down the line, if you come back to your code, it'll be much easier to understand if it's all been well commented, you've given the variables descriptive names, and you've made everything explicit and clear. So just kind of a final thing to remember is that readability does count, but these one-liners will really improve your coding skills, and if you can read and understand these, then reading explicit, well-commented code will be super easy. I really recommend joining Thinkster.com and using the app on there. I've used it myself, and it's made reading source code so much easier, giving me way more confidence, and yeah, just little bits of training every day really just helps you. And then when you come to new code, it's much easier. And if you want to do, take your Python even further, I would really recommend joining the Thinkster Freelancer course. It's a course that I've done myself and I'm still doing, and it takes you from no knowledge of Python all the way up to being able to earn 5 to 10K every single month. I'm on that journey right now. It's why I'm making this video for you. And whoops, I just dropped something. And it really has taken me from working in a job in recruitment in London that I didn't really enjoy to literally traveling the world and being paid as a coder. So cannot recommend it enough. If you have any questions, post them in the comments and we'll get back to you. Thank you so much, and see you next time.